Welcome, everyone. Today we'll be discussing emergency power using a hydrogen refueling station stored supply to run a PEM fuel cell based backup power system. This is the focus of Project 15 Senior Design Project. So let's get into it. Team 15.1 focused on creating a backup power system utilizing entirely new components chosen specifically to handle the load requirements of the station. The team members for this project are
Hello, I am Pedro Villa, and I am an electrical engineer, as well as the team leader of 15.1.
Hi, my name is Sadr Aziza. I am the only mechanical engineering student in this project, and I am working on a thermal management system.
Hello, my name is Robert Quinones, student at Cal State Los Angeles with a major in industrial technology and a concentration in transportation and sustainable energies.
me, Isaiah Glenn, an industrial technology major.
Team 15.2 will focus on creating a backup power system by repurposing a powertrain in fuel cell vehicles taken at the end of the service life in order to power the hydrogen refueling station during an emergency. The team members are
Hello, my name is Marco Cajero, and I'm the project lead for 15.2, and I'm an electrical engineer.
Hello, and my name is Martin Almaraz, and I'm an industrial technology major.
Hello everyone, my name is Francisco Melgar and I'm an electrical engineering major.
My name is Carlos Galdames. I am an industrial technology major. I was the former team leader for 15.2 during the fall semester.
As a refresher, let's take a look at how Cal Citale's hydrogen station works. It uses an electrolyzer to split apart water's hydrogen and oxygen atoms. It then runs the hydrogen atoms through a series of compressors and stores them for later use. During normal operations, we can expect it to create up to about 60 kilograms of hydrogen. When a fuel cell vehicle comes to the station for a refuel, the hydrogen gets sent through a set of high-pressure compressors, after which two parallel chiller units are used to cool the hydrogen before it reaches the dispenser. This is done to meet the vehicle's specific refueling requirements. On a typical day, the station can see anywhere between 5 and 12 customers. Now that we know how the station operates, let's talk about how a fuel cell operates, and ultimately why we chose to use this technology as the primary driver of our backup power system. There are many ways in which a fuel cell can generate electricity, and the differences in their design generally come down to what types of fuel they use. The energy source can vary from natural gases to hydrogen-rich fuels like methanol, or even hydrogen itself, as is the case with the polymer electrolyte membrane fuel cell, or PEM as it will be referred to from here on. Since we're designing a backup power system for a hydrogen refueling station, the PEM fuel cell appeared to be the obvious choice. PEM fuel cells are actually relatively simple in how they generate electricity. They have two sides where hydrogen and oxygen are pumped in respectively. Each of these sides features a gas diffusion layer located just before a platinum catalyst. The catalyst on the hydrogen side of the fuel cell is negatively charged and acts as the anode. The catalyst on the oxygen side of the fuel cell is positively charged and acts as the cathode. The anode and cathode are separated by a polymer electrolyte membrane, which is also sometimes referred to as the proton exchange membrane. This membrane is similarly textured to a thin plastic bag and is non-conductive, which means no electrons are able to pass through it, but hydrogen atoms are free to pass after being ionized at the anode. These hydrogen ions are drawn to the cathode side of the fuel cell, where they're bonded with oxygen molecules, creating water. A single PEM fuel cell is actually very tiny, usually in the order of millimeters squared, and it produces a small amount of voltage, usually around 0.6 volts. This means that in order to get a respectable level of power out of the system, we need to stack a lot of these fuel cells together, creating what is known as a fuel cell stack. The exchange membrane must be kept humidified in order to function, which means some of the water produced can be recycled to help the fuel cell produce even more electricity. Now that we've covered the operation of both the hydrogen station and PEM fuel cells, let's get into our actual project. So what would happen if there was a countywide power outage? Well, there could be dozens of fuel cell vehicles that will no longer have a place to refuel. This is where a backup power system comes into play. Such a system will provide power to the vital components of the hydrogen refueling station, or HRS for short. In such a scenario, based on the data we've acquired, our system would need to support up to 110 kilowatts of power, conditioned to 480 volt, 3-phase, 60 Hz AC. The station will toggle to the BPS with a manual switch. While activated, the BPS will consume hydrogen from the station's storage tanks, and the rate at which the BPS will consume the hydrogen will be dependent on the fuel cell stack that's chosen for the system. It will have 2 inputs and 2 outputs. The inputs will be for hydrogen gas and ambient air, and the outputs will be for electricity and wastewater.
For Project 15, we took 2 different approaches to create such a system. The system for 15.1 will approach the design requirements by using totally new commercial parts to build a system designed to handle the stresses of the hydrogen refueling station. Our team came up with 3 deliverables: research and planning, design and modeling, and project management. With this, we created a Gantt chart for our team in order to set tasks and deadlines to each team member. The cells on the right-hand side represent a single week's worth of time. The timeline begins from August 23, 2020, and ends on May 16, 2021. The task list is located on the left, where each deliverable is shown as a separate color. The tasks are organized by the deliverables, and each is assigned a team member, as well as a start time and an end time. This is shown on the horizontal bars towards the right, which come in 2 colors, gray for a finished task and green for an ongoing task. With this Gantt chart and the weekly advisor meetings, our team had a strong sense of direction throughout our senior design terms. In the fall semester, our team focused on finding relevant research in order to prepare us for the next deliverable in the spring semester. Once we had a solid understanding of the concepts around the project, and we had a catalog of parts we could use as examples, we moved on to the modeling phase. During this time, we researched how to use Simulink and also found pre-made models for us to use as a base version. We were lucky enough to find a few models that were almost exactly what we were looking for. For our final deliverable, we have project management, which was an ongoing deliverable throughout both school terms. This is where all our reports and class deadlines would be, as a reminder of when things were due and also when to meet. Our team decided on 2 weekly meetings with ourselves, 1 weekly meeting with the advisor, and 1 weekly captain's meeting with the team lead from 15.2. Between spring and fall, the days we held meetings changed several times, but we tried to keep the same number of meetings throughout the school term. Of course, we were only half of Project 15, so let's go to Martin to hear how their team managed their part of their project.
Our model will be examining an emergency backup power system utilizing repurposed components from an end-of-life hydrogen fuel cell vehicle. These components are still functional and are viable to second life applications. The application for an emergency backup power system will provide the necessary power to the Cal State LA Hydrogen Research and Refueling Station during the events of an emergency. These emergencies can range from the typical unplanned power outages resulting from potential disasters common in Southern California, such as earthquakes or fires. To understand the backup power system, we will need to introduce commercial fuel cell vehicles, their vital fuel cell components, and the power requirements of the hydrogen refueling station. By recording the operations of the hydrogen refueling station through the hydrogen monitoring system from various dates, we can determine the power demand of the station in both standby and refueling operations. This will ensure we can create a model output to the specifications of the hydrogen refueling station.
During this project, every member had different roles and different responsibilities that match their backgrounds. The project was divided into 4 phases, number 1 being research, number 2 being concepts, 3 modeling, and number 4 being the final report. Phase 1 of the model was research. The goal of this phase was trying to get a foundation on what we're going to do during the rest of the year. We looked to get details on the final goal, how we were going to accomplish this goal, and how we could make it budget efficient. As you can see in the following table, you can see how we broke down responsibilities within the team. For example, the assignment 1.1 hydrogen station details and specifications was given to Martin, Saud, and Marcos with a deadline of 14 days. For phase 2, we work on concepts of the project. The main goal of this phase was to have a model ready on theory that could be followed and applied in real life. As you can see in the following table, you can see the assignments and to whom it was given and the deadlines that were given. For we had 2.1 FCEV vehicles specifications and diagrams with the goal to find diagrams and specifications to commercially available FCEVs. 2.3, creating a black box. This was about building a rough draft of the emergency backup system for the hydrogen station based on research and benchmarking we had done in the past. This was a major deliverable in the project, which is why everyone on the team had to pitch their ideas. The rest of the phase 2 was related to preparing and writing the semester report. Every member was given a part to do depending on the research and findings they had. The third phase of this project was modeling. During this phase, a lot of testing, math, and extra research was done. We used Simulink as the main platform for our testing and simulation. So you can see in the following table how we break down the assignments or the tasks. This was a big phase for the team as a whole. We wanted to implement everything we learned in the previous 2 phases and implement it in simulations. The fourth and last phase was about putting everything together for the final report.
To find what kind of fuel cell and battery we need for the backup power system, we must record the hydrogen station load, in-fueling, and standby operations. Also, we need to understand how much power is being used without the electrolyzer and the low pressure compressor. We also need to know the real power from the base load of the hydrogen station and the voltage requirements needed to power the hydrogen station. The hydrogen station receives its voltage from a 480 VAC 3-phase system. The base real power load of the hydrogen station is 6.455 kilowatt. The base reactive power load of the hydrogen station is 3.741 kilovolt ampere reactive. And the base apparent power load is 7.564 kilovolt ampere. This gives a calculation for the power factor of 0.866. These are important values needed to be inputted into the Simulink model later on. To get any data from the hydrogen station, we need to access the hydrogen monitoring system through TeamViewer. With this program, we are able to record the data necessary by observing the power output of the components and the total power consumption from the hydrogen station under the conditions of fueling or standby operations. As you can see here in this recording, we can see the hydrogen station in the process of fueling from 2 high-pressure compressors. We can see the power output of the station on the top right. You can also observe the power output, pressure, and temperature information from each of the components, like the chiller and the 2 high-pressure compressors. Also, the electrolyzer and the low-pressure compressors are not turned on for this recording based on the power output of the station. From these recorded videos, we are able to sample in small increments for the power output of the components, specifically the electrolyzer and low-pressure compressors, and the total power output of the hydrogen station itself. This will help attain a load profile to reflect the behavior of the hydrogen station in standby or fueling operations, and decide which fuel cell and battery combinations are effective to handle the load. Since the hydrogen monitoring system records the facility's power in real power, we can easily record the data and estimate the daily power consumption of the hydrogen station. Calculating the area under the curve using integration from the charts, we can estimate the daily power consumption of the hydrogen station. This includes the estimate amount of vehicles fueled per day and standby operation power consumption. We estimate a daily power consumption from 42 kilowatt hours to 45 kilowatt hours based on 6 to 10 vehicles fueled per day from video 1. For video 2, using the same parameters, it ranges from 39 kilowatt hours to 43 kilowatt hours. If no cars come by, the daily power consumption is 6 kilowatt hours.
Once we have the power demand of the hydrogen refueling station and we know which components we can use for our system, we can begin to model the backup power system using Simulink. Let's take a look at how to do that. There are several ways to build a backup power system, with several different configurations. But since we are expecting to power a hydrogen station and the hydrogen is lying around unused, we wanted to utilize that resource during the downtime from a power outage. So we decided to go with a model that looks like this. It will have two parallel power sources, a PEM fuel cell and a lithium-ion battery. These units will then feed electricity through a set of converters to give us a single steady DC voltage, which will then be sent to the DC to AC inverter. From here, the system will split the electricity into 3 synchronous phases to match the station's power demands. The battery in the system will require a feedback line which will allow it to recharge from the fuel cell's excess power while the fuel cell is not being used to power the station itself. Now that we talked about the backup system, let's see what the hydrogen station expects in terms of power requirements. The hydrogen refueling station has 2 primary modes that we expect to encounter while the backup system is in operation, a refueling mode and a standby mode. Let's talk about the refueling mode first. When a vehicle comes in for a refuel, the station needs to send hydrogen over from the storage tanks through a compressor and a chiller unit in order to meet the temperature and pressure requirements of the dispenser unit and the vehicle storage tank. This means that the backup system will need to power the station itself, the compressor, the chiller, and the dispenser during its refueling mode. With data gathered from the station at several points in time, we can get a load curve for the station where we can put into our Simulink model. This graph here is from one of those days. As you can see, the black line indicates the load from the station. These are the data points that I talked about earlier. Our goal is to meet that line with our fuel cell and battery, which are represented by the red and blue lines respectively. The fuel cell in this instance has a maximum power output of just under 8,000 watts. So whenever the load from the station exceeds that number, the battery begins to also discharge power. Although when the station's power demand is below the fuel cell's maximum power, the excess energy is diverted towards recharging the battery, which is why the blue line goes below 0 watts at several times. It is drawing energy from the fuel cell rather than providing energy to the station. To avoid overcharging the battery, there is a current limit allowed through the buck converter of the battery. This is why at several points the fuel cell's total power output drops below its maximum value. In other words, the combined power demand from the station and the recharging battery sum up to less than the fuel cell's maximum power output. So the output power from the fuel cell is reduced to compensate. The second mode of operation for the station is while it is idle between fueling operations, which we'll refer to as standby mode. During this mode, the backup power system is not going to be providing power to the compressor or the chiller, and the dispenser and the station are going to be drawing only enough power to stay on. This all means that the power demand seen by the backup power system will only reach up to about 3,000 watts, which we expect to be much less than the maximum output of the fuel cell. During this mode, the battery will basically always be recharging, allowing its state of charge to regenerate from however many fueling operations it had to supplement. If the battery is able to recharge completely, then the fuel cell's power output will only rise to meet the load of the hydrogen station. Based on all of this data, we have figured out that the station during an average refueling consumes about 600 grams of hydrogen. Combine that with a benchmark of the Honda Clarity's 5.46 kilogram fuel tank capacity, and the fact that we would be refueling the tank from near empty to about half full based on safety measures that tell us not to refuel a hydrogen vehicle completely, we can expect to refuel up to about 21 Honda Clarities if they all come in at once. But since that's not really a realistic scenario, a more realistic number is 18 Honda Clarities through about a 3-day period. As I'm sure some of you have noticed, We previously said that the station's true power demand was in the range of 100 kilowatts, not 10 kilowatts as the graphs here show. Since the original model of our current backup system was based on a backup system meant to power an airplane during an emergency landing, the original model had an expected power output of about 10 kilowatts as well. Due to this, we were able to much more easily scale down our components to match the model's original design intentions than to try to upscale the model to meet more realistic versions of the hydrogen station. To rescale the components to the model, our team applied scaling theory, working from the load back to the fuel cell and the battery. With this system, we chose to use a 1/10 scale model for ourselves, since it rounded the two systems together nicely, and also it allowed us to use the AlterG 548 fuel cell as a base model, since its power output is up to 5 kilowatts, 1/10 of the total power we expect the final product of the fuel cell to provide.
Since we are using the same model as 15.1, the only changes would be the block parameters for the fuel cell, the battery, the 4 converters, the AC load, the energy management system, and the protecting resistor. Since it was a modified Simulink model, we adopted along with 15.1 a changelog and note system for each day the model was worked on. This system helps us keep track of various versions of the model and helps us backtrack when a component is not functioning properly. To make sure the system is functioning from our parameters, we need to delve deeper into the energy management system. In the energy management system, or EMS, the entire subsystem directs the load, the DC to DC converter's voltage and current outputs, and the battery's state of charge. It gathers this information from go-to blocks and receives them in from blocks. Inside, the information is then sorted and sent to one of the many subsystems inside the EMS. The frequency decoupling and state machine control block utilizes the power of the load, the state of charge, and the feedback loop to determine the power of the fuel cell in a state machine block. From there, it samples the fuel cell's current through the power of the fuel cell divided by the voltage of the fuel cell. It has some adjustments based off of the minimum and maximum voltage DC bus. It also sets the voltage DC bus to sample charging current and discharging current with the battery's converters. The fuel cell's DC to DC converter reference block receives the output of the sampling fuel cell current and makes 2 comparisons to determine the max sampling fuel cell current. The voltage output for the fuel cell DC to DC converter based on the EMS status being on or off. The fuel cell DC to DC converter reference block receives the output of the sampling fuel cell current and makes 2 comparisons to determine the max sampling fuel cell current. The voltage output of the fuel cell DC to DC converter is based on the EMS status being on or off. The battery discharge DC to DC converter reference block receives the output of sampling battery discharging current and makes a comparison to determine the max sampling battery discharging current. Voltage output and the current output is based on the EMS being on or off. The battery charging DC to DC converter references block uses the same concept, only with the constant voltage output to charge the battery. The protecting resistor block has 2 thresholds to determine whether it will open the circuit or not. It uses a feedback loop in case the voltage does not go below the lower threshold. The load disconnect block has 2 criteria for state of charge and the voltage DC bus. For the voltage DC bus, it must be above the voltage upper threshold to have the EMS on. For the load to be on, the state of charge has to fail its check of being below a certain state of charge comparison, and the voltage DC bus must be above the lower voltage threshold, but not go below it. The feedback loop helps it so it continues to pass a check in case it's not above the upper threshold, but not below the lower threshold. With the parameters set based on the equations and charts provided for the fuel cell and load, let's see how the fuel cell and the battery behave with the varying loads of the hydrogen station. We'll be taking a look at the standby load first. For these following standby charts, they are observed at a full-scale load. For the fuel cell, we can see the fuel consumption is going up along with the current. The standby voltage and current is at 315 volt and 19 ampere, respectively. It also has a steady voltage when the fuel cell power is above the load. The peak consumption for the fuel cell is 12.48 grams and stays between 19 liters per minute to 53 liters per minute. From the power chart, the power output of the fuel cell is the primary source for the backup system, while the battery power output helps the fuel cell during small peaks. We can also observe the extra power from the fuel cell is charging the battery. From the battery, the behavior for discharging and charging is clearly seen. For the majority of the time, the current is below zero, charging the battery with a voltage greater than 265 volts. You can also see this behavior with the voltage and current of the battery as they share an inverse relationship with load demands. The state of charge reaches up to 74% and ends at 63%. Let us continue to observe the model on a fueling condition. These following charts will be at a 1/10 scale. In this fuel cell chart, the voltage is oscillating slightly in response to the load. More information is seen when the current goes past 100 amperes. The peak current is at 127 amperes, and the voltage ranges from 82 volts to 89 volts. From the scaled down power chart, you can see the fuel cell's power output is trying to be a constant source of power, but is able to keep up with the fluctuating load. You can also observe the battery's power output helping the fuel cell reach certain peaks it cannot reach immediately. The scale battery charts show several peaks from the current and dips from the voltage, trying to quickly boost the power based on the load. Battery current peaks at 39 amperes and the voltage dips to 92 volts. The peak state of charge is at 65.36% and ends at 63.99% at the end of the run. These charts are at a 1/10 scaled version of the model in a more realistic approach. In this scenario, we are fueling 2 cars back to back at an approximate 10 minutes of fueling. After the 2 cars are done fueling, the backup system will return to its standby operation. From the power chart, you can see the contrast between fueling and standby in one chart. Let's observe how the fuel cell and battery are behaving in this kind of load. From the fuel cell chart, the fueling portion of the voltage and current are oscillating from the numerous peaks with the current reaching up to 132 amperes and the voltage dropping to 79 volts. You can see it consume about a scale of 20 to 40 liters per minute during fueling. As soon as fueling ends, the current and voltage stay at a constant 20 ampere and 94 volts respectively. Also, the fuel cell consumption drops to 6 liters per minute at this time. At the end of the fuel consumption, the fuel cell reaches its peak consumption at 29.92 grams of fuel. The scale battery chart sees the same situation. We see the inverse reflection of the current and voltage as the battery quickly provides power where the fuel cell cannot handle at the moment. The peak current is at 37 amps and the lowest voltage at 90 volts. We see at a moment where it discharges and charges quickly from 65% to 63% within 200 seconds. Like the standby charts, the fuel cell charges the battery here as well. The peak state of charge reaches up to 78.07% at the end of the 20-minute simulation. The voltage during charging stays above 107 and the current dips to negative 12 amps.
So now moving forward, an important part of the approach was using the theory of scaling. In electric circuits, full-scale circuits can be complex to understand at times. When high voltages and power are being used, things tend to break or short, which is why it is good to scale down to see how a functional model at a lower capacity will work. This system consists of multiple elements that need to be analyzed one by one. These elements as a whole will be analyzed under electrical laws such as Kirchhoff's circuit laws. To fully understand this, we need a mathematical model where we need to change or plug any numbers to a simulation system. The full-scale model consists of a system that could output an average power of 75 kilowatts with peaks of up to 110 kilowatts with AC voltage of about 480. We'll scale down our model to 1/10 of its full scale. Scale down system should output 1/10 of the average power output full scale, which will be 7.5 kilowatt with VAC of 448 with peaks that go up to 11 kilowatts. Some of the benefits from scaling a model is that it can be easier to understand how the system functions. The model could be modified in a specific way to increase or decrease an output, and it's easier to optimize the system later on. So as you can see, the average power is about 75 kilowatts with BRMS of about 480 volts. But instead of using 75 kilowatts as a power value, instead we're going to be using 110 kilowatts, which represent the peaks and therefore represents the worst case scenario. Or current average is, or I average is equal to 229.2 amps. And the scale down average power, what we're looking for it, 11 kilowatt. So as you can see, P is equal to voltage times current or V times I. So if we're going to scale down the power, the output power, we have to divide 110 kilowatts over 10. And these will equal to BRMS times current average over 10. And so we get BRMS over 1 square root of 10 times I average over square root of 10. And so now we have, as you can see the following, we have voltage, and we divide our BRMS of 480 over square root of 10, which will give us 151.8 volts. And the current will be divided by, the current 229.2 will be divided by 10 square root of 10, and it will give us 72.5 amps. So we have B line to line, which is equal to square root of 3 times B line to neutral, and this is equal to 151.3.8, which is our voltage value over square root of 3, and this will give us 87.07. We'll call this BP or B phase. And now to compare this back to DC voltage, in the following equation, you can see that B phase is equal to the B ratio times BC. B ratio represents the ratio conversion of the inverter. This number changes from depending on the manufacturer of the inverter. Now this number 117.6 will represent our voltage at the DC bus, where both the battery and the fuel cell are connected. Both power sources must output the same voltage before they make it to the DC bus, which is why we use DC to DC boost converters to make them match. These converters have a boost ratio which is set by the manufacturer as well. Now to get the required voltage by the fuel cell, we'll do the following. So as we say, the fuel cell boost converter has a 21% boost ratio, and therefore we have the BDC, which is the voltage at the DC bus, equal to the voltage output from the fuel cell times the boost ratio. So to get the voltage from the fuel cell, we'll have to divide the fuel cell, the voltage fuel cells over the boost ratio. This will be equal to 117.6 over 1.31 This will give us about 89.8 volts or 90 volts. For this, we can conclude that the stack has to output about 89.8 volts. There are many ways a fuel cell stack can have its voltage modified. However, depending on the manufacturer, it will be stated what they can output.
The purpose of the thermal management system in this project is to design a cooling system for the fuel cell stack in the backup powered system to reject sufficient heat. I chose 90 and 30 kilowatt fuel cell stack from Hydrogenics to design the cooling system. The requirement we need for the cooling system for the 90 kilowatt model is 160 kilowatt heat rejection, and for the 30 kilowatt model, we need 30 kilowatt heat rejection. For both models, we need cooling temperature between 50 to 70 degrees Celsius. For modeling, I found engine cooling system demo, and I adjusted it by removing the oil pump, which was driven by the engine, and I have removed the oil loop in the engine, and I have added constant flow going to heat source. I simplified the fan and removed the fan control and applied fan speed. Based on the parameters given by Hydrogenics and my calculation, I have changed the inputs of the radiator, thermostat, coolant pump, and fan speed. I ran the model for 5,000 seconds for both models at 160 kilowatt and 120 kilowatt for the 90 kilowatt model, and 30 kilowatt and 20 kilowatt of heat flow for the second model, under 45 degrees Celsius of ambient temperature. As shown in the graph, the cooling system succeeded in both cases in keeping the cooling temperature between 52 degrees Celsius. Here are the recommended equipment based on my calculation for heat exchanger and fan by dry cooler. For the pump, I selected model based on the minimum head requirement, which was calculated to be 8 meter and flow rate at 109 liter per minute, which was around 30 GPM. Thank you.
Economic sense. Why did we choose to repurpose fuel cell vehicle components rather than acquiring a new fuel cell with maximum efficiency? Well, the answer is sitting behind the economics and as well as the obstacles and challenges facing fuel cell technology. In order for fuel cell vehicles and their systems to make a deeper impact on the market, we need to understand the opposing challenges. That would be the lack of hydrogen infrastructure available, and secondly, the manufacturing cost of fuel cell technology. For the purpose of this project, we'll focus on the manufacturing costs of a fuel cell vehicle alone and explain how significant establishing a repurposing and recycling process for fuel cell components would be for energy sustainability. In the instance for the fuel cell vehicle, we will be repurposing at its end of life cycle a 2017 Toyota Mirai. Its initial upfront cost to the consumer was $57,500. If we compare this fuel cell vehicle to, for example, a 2017 Toyota Prius costing around $23,000, we can see that there's a gap in price difference due to the powertrain behind both vehicles. The Prius and the Mirai share many components and systems, such as a high voltage system, except for an estimated $35,000 fuel cell system. For our objective, the fuel cell vehicle we'll be repurposing will be a 2017 Toyota Mirai at its end of life cycle. The average difference in price between the 2017 Toyota Mirai and the 2017 Toyota Prius is estimated to be $35,000. We can assume that the price difference is a cost for the fuel cell system alone, because the Toyota Mirai's high voltage system is based on the Toyota Prius, from its lithium-ion battery to high voltage wiring to the inverted assembly in order to mitigate any additional manufacturing costs for the vehicle. If we see Table 1 provided to us by an article written by Olivier Bidox, we can analyze that from a fuel cell system with a net power of 80 kilowatts, about 50% of the cost distribution is on the fuel cell stack alone. If we use the provided ratios of cost distribution for a fuel cell system and compare it to our vehicle, the Toyota Mirai has a fuel cell system with a net power of 114 kilowatts. We can assume that 50% of the cost distribution for the fuel cell system is equal to $17,500 for the fuel cell stack alone. Moreover, if we dive in further into the cost distribution of a fuel cell stack, we can observe from Table 2 that 51% of the cost distribution is on the active layer, which contains all the platinum necessary to effectively complete the chemical reaction that generates electricity. Then we can also observe that 24% of the cost is on the bipolar plates, which entails costly special corrosion protection coatings with excellent thermal and electronic conduction properties. The 24% cost of the bipolar plates can be reduced with the use of other metals such as untreated stainless steel, which Hyundai is currently experimenting with the Nexus fuel cell. So there's a very high possibility to mitigate this cost of the bipolar plates, but compared to the active layer that accounts for 51% of the cost distribution, it is very unlikely that cost will decrease due to platinum. Platinum is a critical rare earth metal that its supply is at risk due to its scarcity and geographically poor distribution. Additionally, to extract platinum from the Earth's crust involves high environmental impacts, including emissions of sulfur dioxide, of carbon dioxide equivalents in the range of 13,000 tons per ton of platinum, excessive water consumption, energy consumption, habitat destruction, air and water pollution, solid waste, and hard mining conditions, which results in platinum's prices to remain high and a major barrier to the fusion of fuel cell technology. Due to the platinum's high price, it would be critical to establish a repurposing and/or recycling process to satisfy the industry's need for platinum. The automotive industry is the largest net consumer of platinum, accounting about 36 to 46%, and only about an estimated 50 to 60% of exhaust gas catalysts are recycled. If we put in perspective that a fuel cell vehicle uses 10 times the amount of platinum than an internal combustion engine, it would be in the best interest for both the fuel cell and automotive industry to create an established repurposing and recycling process to meet future platinum demands. For the repurposing process, we would have to analyze the existing recycling chain, which entails 4 processing steps: collection, dismantling, disassembly and pre-processing, and material recovery. Then follow the necessary steps to repurpose a fuel cell vehicle. For repurposing a fuel cell vehicle, our team would be involved in the collection, dismantling, and disassembly process in order to retrieve our fuel cell components accordingly. The vehicle will be sent to a junkyard for further disassembly, pre-processing, and material recovery afterwards. For repurposing a fuel cell, the first step will be collecting the vehicle, and this may be from a leased program of end-of-life fuel cell vehicles, or possibly a total fuel cell vehicle. Depending on its condition, the fuel cell components may still be usable. Then the second step would be dismantling the fuel cell vehicle, and this will be done manually to prevent any damage to the fuel cell stack. While following all California OSHA and National Highway Traffic Safety Administration guidelines regarding electrical safety and isolating high voltage systems, we would remove all necessary equipment to access the selected fuel cell components. This would involve the removal of the vehicle subframe in order to get access to the fuel cell components for removal. For the purpose of this project, we will be removing the lithium-ion battery and the entire fuel cell system, excluding the hydrogen storage tanks, in order to create our fuel cell backup power source. Now that the rest of the vehicle is stripped from its components, it may be sent to the junkyard to be shredded and recycled for its leftover metals. Providing the fuel cell system a second life application will eliminate further accrued costs from manufacturing a fuel cell stack, and especially reducing the environmental footprint of obtaining such platinum metal groups. Establishing such a process for fuel cell technology would be a significant push forward towards energy sustainability. After the second life application of the fuel cell has reached its complete end of life, passing 10% efficiency, then we can continue with the recycling process to retrieve the platinum metal groups, but for the purpose of our project's objective, we'll leave it at the second life application of a fuel cell vehicle.